Okay, so let us discuss about the lightning protection. So, objective of this video, we will discuss about the different technique, different standard that we use for the lightning protection calculations, and this video is useful if you are uh, going for the interview for the as electrical design engineer, and if the questions coming on the lightning protection, so how we will respond at that time. So if the question coming on the lightning protections method, or sometimes it is called as the DSLP also, direct stroke lightning protection. So for the lightning protections, there is three techniques overall we use. One is the IEEE 998 method, IEEE 998 standard. Second is the IEC based standard, IEC 62305, and third is the Professor Rajvik. So first of all, we should know all the applicable standards. This is the first input, first knowledge we should have. IEEE 998, I again repeat, IEC 62305, and Professor Rajvik. The European country work on the IEC based standard. The American country work on the IEEE based standard. And this is a separate book that also suggests for the lightning protections calculations. And one more thing, this IEEE 998 have this standard have the two method. First is the rolling sphere method. Rolling sphere method. And second is the fixed angle method. The fixed angle method is very easy. Just we take this structure, steel structure, and this steel structure height should be higher one, or we can install the another dedicated structure for this, and we place the lightning rod here on this steel structure. And the IEEE is telling that this lightning rod will provide the protections based on the angle, whatever the area coming on this angle, so this area will be protected by that rod. And suppose some area left not protected by that angle, so we placed another steel structure, and on that we place another lightning rod, and then we again take some area. So what is the this angle of protection? So let us see what is the IEEE recommendations. So this is IEEE recommendations. I have taken the particular page from the IEEE fixed angle method. The angle used are determined the degree of lightning exposure, the importance of the substations being protected at the physical area occupied by the substations, the value of the angle alpha that is commonly used 45 degree. So this is telling that this angle is called alpha, and this will be 45-degree angle, here 45. So inner angle, you can see, we can remember like this: inner angle 45 degree, and the outer angle is 30 degree. Both 30 degree, commonly used 45 degree. Both 30 degree and 45 degree are widely used for the angle beta. So let us check what is the angle alpha and beta through this standard. And one more thing, this 45 and 30 degree is not common for every structure height. This is limited. If the structure height or the lightning protection height is up to 15 meter, then only this 45-degree angle is applicable. If the structure height, if a structure height increased from 15 to 25 meter, in that case this angle will be reduced. So let us come on this. This is lightning struck rod, here lightning rod. This is alpha angle, this again alpha angle, and beta angle, outer beta angle. So what, from here to here, this is the protected object. So whatever the area covered by this angle, this is telling that it will be protected by this structure. So this is basically the fixed angle method. That is very easy method, fixed angle method. Only we calculate the 45-degree angle and 30-degree angle. We cover the area and we say that this area is protected. Now in case of the rolling sphere method, how we proceed for the rolling sphere method? In rolling, let us discuss this rolling sphere method with some my project calculations. I have taken this rolling sphere method for one of the 220 kV based substations. This rolling sphere method involves the BIL level of the substation, and in this rolling sphere method, and a reference is IEEE 998, we calculate the corona radius RC by this formula, and this is corona radius we calculate. We take the equation C.1 of annexure C in IEEE 998 to calculate the corona radius. Thereafter, we calculate the surge impedance under corona ZS by using this formula, equation number C7, page 133 of the IEEE standard 998. So basically we calculate the corona radius, surge impedance under corona, and we calculate the critical stroke current. Critical stroke current and sphere radius. So for the critical stroke current IS, this is 2.2 into BIL divided by ZS, 2.2 into basic insulation level. Suppose this is 220 kilovolts, so 1050 is the basic insulation level. So 2.2 into 1050 divided by ZS, that we have calculated here, and we calculate the critical stroke current, that is coming 6.45 kiloampere by using this formula of the IEEE. Thereafter, we calculate the striking distance or the radius of the sphere by using this formula. So this is the striking distance. So we can say in the rolling sphere method, if we summary all the steps, first we have to reply that we calculate the corona radius, that is RC, and we calculate the surge impedance during the corona. Surge impedance during corona. Thereafter, we calculate the critical stroke current, critical stroke or striking current IS. IS same formula, the V is equals to IZ. So I we wanted to calculate, so VYZ. So here we do 2.2 into BIL. This is also voltage divided by the ZS. And thereafter we calculate the rolling sphere radius. Radius of the rolling sphere. Radius of the rolling sphere. So this 4 steps we follow. Corona radius RC, surge impedance during the corona, lightning current, critical striking current, and the striking distance are the radius of the rolling sphere, and how it provide the protections. So again let us see the IEEE applicable clause. So this is the striking rolling sphere, and there this rolling sphere radius we calculated. We roll this sphere through the substations going up and over the shielding electrodes. This is my shielding system here, here, here and here. So we roll this rolling sphere on the substations, on the substation, and through the shielding electrodes, through the shielding electrodes. And we say that whatever the area coming below that sphere, it will be protected from the lightning. So let us again repeat what is the rolling sphere. In the rolling sphere, we calculate the corona radius, surge impedance during the surge impedance under the corona, and critical lightning stroke current and the radius of the sphere, and we roll this sphere on the substation and over the shielding electrodes, and whatever the area covered under this sphere, it will be protected. So this is how this IEEE 998 tell about the lightning protections. Now let us discuss about the IEC 62305. What is their approach for the lightning calculations? So in the IEC 62305, for the lightning protections, we take up as input the thunderstorm days per year and lightning density of that locations. Let us discuss this lightning protections through some project. This is a 220 kV GIS substation, and this calculations for the GIS building. So how we have performed here this lightning protections calculations. So IEC need the highest possible class of lightning protection system. So reference IEC 62305. This 62305 total have the four number of part. Part 1 general principle, part 2 risk management, part 3 physical damage to the structure and the life hazard, and part 4 is the electrical and electronic system within the structure. So this IEC all part 4 we have utilized, and the 220 kV GIS building layout plan and section drawing. So what is the input? We required the GIS building and thunderstorm days per annum. This we required, and lightning density. This lightning density we can calculate by the formula 0.1 into TD. TD is the thunderstorm days per annum per year. So this is the input that we required, and thereafter during the calculations we calculate all type of the losses due to the lightning. So let us see, and before doing the calculation of all type of losses, we calculate what is the collection area on which the lightning can come. So we calculate the collection area A. So this is the collection area, all we have calculated. Now this collection area have different, like the area of the structure, area of the adjacent structure. So this all we have to cover. So we calculate the collection area. So if we overall take so far, we take input as the lightning thunderstorm days per annum. Thereafter thereafter we calculate the lightning density 0.1 into 2 TD by this formula, and we calculate the collection area. Thereafter, collection area calculation, we identify all type of losses and estimate all type of the losses that may occur on the GIS building or on the structure. So this is the source of the damage. So we identify all type of losses and we estimate the overall risk of the from the lightning. We calculate the overall risk, that is called the R, overall risk value R, and we compare this overall risk value R by the tolerable risk value RT. So let us check. These all probable risk we have calculated. By these all steps we reach to the overall risk R. This risk, and thereafter we compare this calculated risk R with the tolerable risk value. If the calculated risk R is less than 10 to the power minus 5 per year for loss of human life, we can see here this is 10 to the power minus 5, and this is the acceptable risk, and this is the calculated risk. So if the calculated risk is less than the tolerable risk, then lightning protection is not required. And if the calculated risk exceeds from the tolerable risk value, in that case the lightning protection is required. So for the losses, there is four kind of losses IEC suggest: loss of human life, loss of service to the public, loss of cultural heritage, and loss of economic value. For the human life, this is very high, 10 to the power minus 5 per year we take as a tolerable value, and the calculated value is coming like 0.35. So this is here the calculated value is exceeds from the tolerable value. In that case, we are telling that lightning protection system is required. In other cases, for the loss of service to the public, this is 10 to the power minus 3, and loss of cultural heritage 10 to the power minus 4. So these all is the value, is the tolerable risk value, and we calculated risk value here. We calculated based on the formula of the IC, and we compare both the value, calculated overall risk value with the tolerable risk value, and after the comparison we establish that whether lightning protection system is required or not. So here we can see that this overall calculated risk value is coming higher than the tolerable risk value. In that case, the lightning protection system will be required. Hence, lightning protection system is required. This is one conclusion. And after establish that lightning protection system is required, after this determination, after this calculations, how we provide the lightning protection system. So there is 4 level of the lightning protections and 4 class for the lightning protection system. As we can see here, lightning protections level 1, 2, 3 and 4, class of lightning protection system, total 4 classes, and which class we choose, it depends on the lightning density value. So in my case, based on the location of the substation, the lightning density was very less, 36. So when the lightning density is small, then we start from the class 4, and if higher, then we start from class 3. So in the class 4, based on this class, what we determine, based on this class we determine the rolling sphere radius and the mesh size, the mesh that we make upon on the GIS building roof. So the rolling sphere radius, if the class 4 then 60 meter, if class 4 then 60 meter, and the mesh size is 20 by 20. If class 3 then 45 meter, mesh size is 15 by 15. Similarly class 2 30 meter and 10 by 10. So if we can see here, if when the classes increased, then the mesh size also, this mesh size reduced, we have to take more conductor here. So this is the estimation of the mesh size, and we make the 15 by 15 or 20 by 20 mesh on the roof. And how we calculate the number of down conductors? So for the down conductor calculations, we calculate the total peripheral of the building. For the peripheral, that's 2 into length plus width. So here we calculated the total perimeter of the structure of the building, L plus W into 2, and divide by the total typical distance of the mesh. So L plus W into 2, it is coming around 66.46 divided by 20, this mesh size, and it is coming around 3 point something it will come, but we will take next standard 4 value. So total number of down conductor is the 4, and the mesh size is 20 by 20. We have to place it on the top of the building. So this is the method of the IEC 62305. And in case of the Rajvik, so we take LM method, 1 LM method, 2 LM method, 3 LM or 4 LM method, and from the 1 LM method we calculate the protection radius of the single LM. If through this single LM the entire substation area is covered and protected, then 1 LM is sufficient. If not, some area left, then we go on the 2 LM method. In 2 LM method we calculate the combined radius of protections, and we take one imaginary element on the center of the both element, and we find out the midpoint protection height and the radius. If some part left, then we go on the 3LM method. Similarly, in 3LM method, first we calculate single element protection area, thereafter we go on the combined protection of 2LM here to here, here to here, and similarly here to here, and we say that so all area covered by here it will be protected, and we say that any circle passing through this 3 point, so whatever area covered inside this circle it will be protected. And thereafter we go on the 4LM method. In 4LM method there is 4 LM we placed on the corner here to here. First here we take 1 LM method, single LM method, then here to here combined 2 LM method, here to here again 2 LM method, again 2 LM method, and again 2 LM method. And this Rajvik equation is telling that if the distance between the two largest LM is less than A into P, so this all 4 LM will provide the combined protection. So whatever area coming here, it will be protected. So this is the Rajvik equations method. In IC, we discussed that in the IC we calculate we take the annual thunderstorm days per annum. This is the first input. Thereafter we calculate the lightning density Ng. This is 0.1 into Td. This we call as the Td. Thereafter third we calculate the collection area, Nc, collection area. Thereafter we calculate or we identify all type of losses. We identify all type of losses and we calculate the overall probable overall probable risk value R, and this overall probable risk value R we compared with the RT. RT is the acceptable risk value. If R is exceed from the RT, in that case the lightning protection system is required. If less, then it is not required. And when it is required, then there is again 4 class we have, and based on the classes we have the protection, uh, rolling sphere radius and the mesh size based on the classes. So if it is required, then thereafter we select that what is the LPS class we wanted to take. There is 4 class, 1, 2, 3 and 4. In fourth class, every class has a different mesh size and the rolling sphere radius. So based on the lightning thunderstorm days are based on the lightning density, we select. If this value is less, then we start from the class 4, and if value higher, then we start from class 3. And if we are going to class 3, then it will be 15 into 15 meter mesh we have to make. So this 3 standard we follow if we overall conclude this lightning protection system. So for the lightning protection system, we follow 3 method: IEEE 998, IEC 62305 and Professor Rajik equations. If we are going for any company that is MNC company, so we can, like Professor Rajik, we can avoid to say, or we no need to say, because this is not the IEC or IEEE standard. This is a particular book for the lightning protections calculations. So in IEEE 998, there is 2 method again: rolling sphere method and the fixed angle method. In the rolling sphere method, we calculate the corona radius, surge impedance during the corona. Thereafter, we calculate the lightning stroke current, and we find out the radius of the rolling sphere. And this rolling sphere we move on the substations through the shielding electrodes, and whatever the area coming below that rolling sphere, we say it is protected. Yeah, IEEE said it will be protected. And in the IEC 62305, based on the LPL lightning protections level or LPS class, this standard is defined the lightning protection system. Okay, so thank you. If any doubt, you can uh, message me separately and through my WhatsApp number. If any further, or if any further clarifications on the lightning protection system required, or if any drawings or Excel sheet how to calculate, so you can reach to.